Hello, welcome to lecture 29 of the course. We'll continue our discussion on cavity quantum optomechanics. In this lecture, we'll study the linearized optomechanical Hamiltonian and study phenomena such as ground state cooling of the mechanical oscillator, squeezing, state transfer, and optomechanical entanglement, and so on. So, let's begin. In the last class, we have started discussing the optomechanical Hamiltonian. This optomechanical Hamiltonian can be written in two forms. In one form, you can write down the energy of the mechanical oscillator in terms of momentum P and the position operator X, or you can write it in terms of the creation and annihilation operator, that means B dagger B. Now, this particular equation can be diagonalized using the polar return transform, and that we have done in the last class. And using this Polaron transformation, we got this Hamiltonian, and which, as you can see, is diagonalized, and the energy eigenvalues is given by this expression here, where h per omega 0 Na gives the energy of the photons, and h per omega m nb gives the energy of the phonons, and this is the energy that is arising. The last term is arising due to the interaction between the photon and phonon, and that is because of the coupling basically. And it also shows one fact that if this coupling is not there, then this photon and the phonon, both of them are behaving like individual harmonic oscillator, but because of the coupling, this harmonic oscillator ladders is now getting broken, and anharmonicity is entering into the picture here. And what we have also analyzed, and we found that the optical mode sees a intensity dependent phase inside the optical cavity, and which is called the Carr effect. Okay, then we have taken into account the laser drive also, or equivalently we have written the Hamiltonian in this form. And here we are considering the rotating frame of reference. The frame is rotating at the laser frequency, and this one we have analyzed, and we obtained the so-called quantum Langevin equation, writing down the Heisenberg equation and then adding the noise terms phenomenologically. For example, here in this expression, you see that this noise term given by xi is added here, and that is the Langevin noise which enters into the system from outside, and the mechanical oscillator is decaying at the rate gamma m, and the optical cavity is decaying, optical amplitude, the cavity mode is decaying at the rate kappa by 2, and also from outside the vacuum fluctuation is also entering, that is also getting that is a noise, that is a quantum noise, that is also taken into account. So this set of three equations are called quantum Langevin equation, and this noise, quantum noise, they have zero mean, as I have shown by this expression, and they satisfy certain correlators, and these are the correlators they satisfy, both A and A in and this Langevin noise. In fact, what is to be remembered here, for example, this xi of t dash is equal to this expression. Physically, it means that the is interaction of the environment or the bath with the optomechanical system via this Langevin noise xi is correlated only to itself, because it is delta correlated. So it is correlated only to itself and to no other interactions. So the environment or the bath, this environment is also known as bath, it is Markovian. This basically means that it is, this correlation is dependent on the present time only, it does not involves whatever is happening in the past. Okay, so that's why this is, in these interactions are, these quantum noises are assumed to be Markovian nature. Then we went on to study the steady state solution of these quantum Langevin equations, and then steady state solutions are for the optical mode it is alpha bar, for momentum it is p bar, and for this position Now we are writing the position as q rather than x. Okay, so position steady state value of the position is q bar. Then these are the solutions we obtain. P bar is equal to 0, q bar is given by this expression, and alpha bar is this. Then we went on to study the linear response of the optomechanical system around this steady state values, and what is assumption, the answers that we are taking is that this A is deviating from its steady state value by delta A. This is the quantum fluctuation, and similarly for Q, this fluctuation is delta q. For p, the fluctuation is delta p. And inserting these answers in the quantum Langevin equation and then discarding the nonlinear terms, because these fluctuations are very small, so the nonlinear terms are going to be extremely insignificant. So ignoring these nonlinear terms, we obtain this set of three evolution equations for these fluctuating operators q, p, and a. These are the equations we obtain. Here this z is equal to z0 alpha bar, that is the linearized optomechanical coupling, and delta dash is the effective detuning. And we can actually write these equations in the linear regime in terms of exclusively in terms of creation and annihilation operator also, rather than in terms of q and p as we have written here, as you see. So we have to then take this particular Hamiltonian into consideration, and if we take that a is equal to alpha bar, which is the steady state, and it is deviation from is the steady quantum fluctuation is delta a. Similarly for beta b, the annihilation operator for the mechanical oscillator, the steady state value is beta bar, then its quantum fluctuation is delta b. And then if we do the analysis in the similar way, we are going to get this set of two coupled differential first order differential equation in the linear regime. And because of these equations, we can write a linearized optomechanical Hamiltonian, and this is what we obtained finally in the last class, that this is the linearized optomechanical Hamiltonian. Now as you can see, rather than writing the symbol delta A or delta B all the time, so this time what we are going to do, because now onwards we are going to work on the linearized regime only, so we are going to replace delta A by simply by A, and delta B by simply B. Okay, so in that case our linearized optomechanical Hamiltonian that we are going to consider now onwards should be minus h bar delta, and even delta dash I am now writing as simply delta, because this delta and delta dash are nearly the same. So let me just write it as delta, and here I have a dagger a, and I have the second term is h bar omega m b dagger b. Okay, and the last term is h bar z b plus b dagger into a plus a dagger. Okay, this is what we have, and this is the most important Hamiltonian that we are now going to deal with. This is called the linearized optomechanical Hamiltonian. Some physics hidden in the linearized optomechanical Hamiltonian can be captured by this very meaningful schematic. As you can see here, we have two coupled oscillators A and B. Coupling between them is Z. The oscillator A, the optical cavity, it is decaying at the rate kappa to a zero temperature bath or environment, while the mechanical oscillator is decaying at the rate gamma m, and it is coupled to a finite temperature bath. The optical oscillator is oscillating at the frequency minus delta, and the mechanical oscillator is oscillating at the frequency capital omega m. And because this oscillator has positive frequency, so we should have minus delta should be greater than 0, and omega m is obviously greater than 0. Now you see the optical oscillator is connected to the temperature is vacuum, which is at temperature 0, and the mechanical oscillator is connected to a finite temperature. So what happens in because of this coupling is that the temperature of the mechanical oscillator come down provided we have minus delta is greater than 0. This means that delta is equal to omega L minus omega 0, right? And that should be greater than 0. That means we should have omega L should be less than omega 0. That means the laser radiation has to be blue detune, red detune. Laser is red detune. If the laser is red detuned, then we can have this situation. We have a positive oscillator, optical oscillator, and a mechanical oscillator, and when they couple to one another, the temperature of the mechanical oscillator basically drops down, and this is the phenomena called optomechanical cooling. However, to get a more better understanding, let me consider the fact that the formula to give the number of thermal quanta, as you know, is given by this expression nth. I think if I analyze using this formula, things should be more clear to you. We have 1 divided by exponential h bar omega by kBt. This is the thermal phonon number formula, and we know this formula. Now let me analyze it for the case of the optical mode first. So for the optical mode, we have omega, this frequency is on the order of 10 to the power 14 hertz, and at temperature, at room temperature, say at temperature 300 degree Kelvin, if you do the calculation, because kb is the Boltzmann's constant, and if you put the value, then you can estimate that nth, that is the thermal photons, is going to be around 10 to the power minus 35. So this is nearly equal to 0. That's the reason when I have drawn this diagram here, you see the optical oscillator is connected to vacuum at temperature 0. So optical mode is effectively at 0 temperature. On the other hand, if I consider the phonon mode, let me write here phonon mode or the mechanical oscillator mode. A mechanical oscillator oscillates in the frequency range between 1 to 1000 megahertz, and if you put it again the temperature at around 300 Kelvin, and if you do the calculation, then this thermal phonon number turns out to be in the range of 10 to the power 4 to 10 to the power 7. So it's not 0, and it's a very good, it's a large number. This is why optomechanical system at optical frequency, the thermal photon numbers can be neglected, but the thermal phonon population has significant effect, as the formula says, as we have shown you. And this is the reason why one needs to cool the mechanical oscillator to its ground state to exploit the quantum effects properly. As you can see again from this schematic, let me tell this thing to you once again and emphasize this fact that for cooling to happen, this detuning parameter has to be less than 0. Okay, so for cooling to happen, for cooling of mechanical oscillator, you should set the detuning parameter to be less than 0. That means the laser should be red detuned. This implies the laser has to be red detuned, and this is extremely critical to cool the mechanical oscillator. Now let me understand this optomechanical cooling phenomena a little bit more intuitively, and we can understand it by assuming, let me just first let me discuss very qualitatively. Let's say we have this optomechanical system is we are having, and a photon is getting incident on this optomechanical system, and this photon has a frequency omega L which is less than omega 0. Now you see that if this photon can enter into this Fabry-Perot cavity, it has to satisfy the cavity resonance frequency. That means when omega L is on the order of omega 0, if omega L is equal to omega 0, the photon can enter into the cavity. Photon can enter into the cavity, because now the photon has less energy than that of the optical cavity, the cavity photon, right, omega 0. So it has to arrange this extra amount of energy from somewhere so that it can make up for the deficit energy, and then it can enter into the cavity. The laser photon does it by extracting if it can extract some amount of energy from the mechanical oscillator or the phonon, then it can enter into the cavity. So this deficit energy, if it extract from the phonon, the mechanical oscillator, and in the process the mechanical oscillator gets cooled, and this process is called anti-Stokes process. Anti-Stokes process. Anti-Stokes process. And here what happens is that the photon, the laser photon, let me say, or say the energy is getting extracted from the mechanical oscillator, and thereby cooling the mechanical oscillator. I hope you get the idea here. And similarly, you can understand the other process when, say, we are now having a situation where this laser photon has energy, omega L is now, say, greater than omega 0. Earlier we considered omega L less than omega 0. Now this time omega L greater than omega 0. Now this time also it cannot enter into the cavity because it has excess energy. So it has to set some of its energy so that it can omega L is equal to omega 0. So this particular thing that I have written here is valid in this situation also. So that the laser photon can enter into the cavity, it has to set some of its energy, and generally what happens is that this energy is getting dumped to the mechanical oscillator. That means the mechanical oscillator extract energy from the optical photon, thereby the mechanical oscillator gets heated up, and this process is called Stokes process. And in the Stokes process, the mechanical oscillator gets energy from optical photon. Okay, and in this process, this is called Stokes process. In the Stokes process, the mechanical oscillator gets heated up, and on the other hand, in the anti-Stokes process, the energy is getting extracted from the mechanical oscillator, thereby reducing its temperature or making it cooler. Okay, so this is the physics behind this optomechanical cooling is. And also you see that to have a dominant anti-Stokes process so that we can cool the mechanical oscillator, the laser needs to be red detuned. That means we must have delta less than 0 for cooling, and this you should all remember, or in other words, that laser must be red detuned. If the laser is blue detuned, then the mechanical oscillator gets heated up. If the laser is red detuned, then the mechanical oscillator cool down. To get a more quantitative picture and to understand the quantum limit of optomechanical cooling, let us now discuss what happens to the mechanical oscillator in the presence of the cavity, presence of the optical cavity. We are going to consider the mechanical oscillator as our system and the optical radiation or the optical cavity as the environment. If the mechanical oscillator is in say one photon state, it is say in one photon state, then it may decay to the zero photon state, that means K0, at a rate gamma minus. It may go to the downward direction, it may decay to the ground state at a rate gamma minus. But if it is already in the ground state or K0 state, then very rarely it can also take energy from the optical cavity and go up with a at the rate gamma plus. That means it may do an upward transition. In the end, this is the balance between these two rates that decides what happens. For cooling to happen, it is clear that the downward transition must dominate over that of the upward transition. That means the downward rate should be greater than the upward transition rate. Now from quantum mechanics, we know that a quantum system that is getting coupled to some environment, the Hamiltonian is generally of the type of this type, and here this X operator refers to the system and F is the fluctuating operator belonging to environment. So this is the fluctuating operator belonging to the environment. We can calculate the transition rates within the system, say from the initial state ket I to the final state ket F, by applying the so-called Fermi golden rule. So the Fermi golden rule, which you may have encountered in your quantum mechanics course, is given by this formula here, and I will explain what it basically tells you. Gamma I to F is the transition rate. Transition is happening from the initial state ket I to ket F. So that rate is given by this gamma, and it is equal to 1 by h bar square, and then the modulus of this matrix element of the system operator. This is the matrix element of system operator, and then it is multiplied by the spectrum of the fluctuating environment. This is the spectrum. I will also explain what this term is. This is the spectrum of the fluctuating environment or the fluctuating operator belonging to the environment, and it is calculated at the frequency omega is equal to energy difference between the initial state and the final state divided by h bar. Okay, and this spectrum, which is also sometimes denoted by this symbol SFF at frequency omega, is nothing but the Fourier transform of the correlator of the fluctuating operator. Now for our present case, we have our system as the mechanical oscillator and the optical cavity part belonging to the environment. So you can figure out what is your X and what is your F here in the Fermi golden rule formula. You can put it accordingly to calculate the various rates. For example, we can find out the downward transition rate gamma minus, and the transition is happening from the happening between, because I am interested in the downward transition rate, so it is going from the one phonon state to the ground state 0. So therefore this matrix element I have to calculate, and then I have to calculate this spectrum as well belonging to the optical cavity. So this first term, this particular part is easy to calculate. As you can see, this is simply going to give you z square. Z is the linearized optomechanical constant, and SFF is the spectrum calculated at the frequency plus omega m, because the energy difference between the mechanical oscillator energy levels, the one photon state and the ground state, is omega m. The frequency difference is omega m, as we know. So using this, we have to calculate SFF at plus omega m. And to calculate this particular quantity, first of all we have to deal with this commutation, not this commutation, this expectation value of this operator a plus a dagger, a plus a dagger, and you have to work it out at time t, and a plus a dagger at time t and a plus a dagger at time t is equal to 0. If you take the product, you are going to get 4 terms. Out of these 4 terms, most of the terms, all the 3 terms are going to go to 0, and only the term that is going to survive is this particular term. Because we are calculating why this all the 3 terms vanishes, because this you have to calculate the expectation value with respect to the ground state. Okay, because you remember that we have replaced delta A by A, and delta A is nothing but the quantum fluctuation around the steady state. So it's already in the ground state. This optical cavity is already in the ground state, and also you remember that optical cavity was coupled to the vacuum, that means the ground state. So therefore you have to calculate the expectation value with respect to the ground state, and if you do the maths, then only term that is going to survive is this final term. Now from the rate equation for this optical cavity, which is the environment, we have this particular equation. In the absence of the mechanical oscillator, if I don't consider that part, then this is what I have. And environment is anyway, it's a big system, so we can ignore the other part while dealing this evolution equation for this optical mode. And the solution of this optical mode is simply this one. This is the expression you are going to get, and it's trivially you can see. Then if you put it here in this expression, then this term will come out, and then you have to then work out the expectation value of A0 and A dagger 0 with respect to the ground state, and that's simply going to give you equal to 1, right? Then with this, we are now having the spectrum as will be left out with this particular integral. And because of the fact that this part is giving us this term here, and if we put that this integral, we have to evaluate, and evaluating this integral, you are going to get SFF. The spectrum at the frequency omega is found to be this simple expression. However, we are interested in calculating the spectrum at the frequency omega is equal to plus capital omega m. So therefore we just have to replace this omega with capital omega m, and then this is the spectrum at plus omega m, and this is going to give us the rate gamma minus, and gamma minus is given by this particular expression here. And in the similar way, you can calculate the upward transition rate also, gamma plus, and gamma plus is given by this particular expression. In fact, you can put the spectrum, you can plot the spectrum as a function of frequency, and this is what you are going to get. And you can do that for delta less than 0 when this laser radiation is redetuned. Then you are going to get this plot. From this plot you see that peak is around omega is equal to this minus delta, and that is you can actually do it carefully, and you can see that this is what you are going to get. So basically what we are doing, we are plotting this expression here. Okay, this is what we are plotting, and the width of this spectrum is kappa, and that is related to the cavity decay. That's the full width at half maximum. And if I just pick up this particular point, and also you see the bulk of the spectrum lies towards the right, and also it is very clear that at the frequency say omega m, the transition plus omega m, the downward transition rate is much higher than the upward transition rate, gamma minus is greater than gamma plus, that refers to cooling. Then you can also go on to calculate the average phonon number. To calculate the average phonon number, you can utilize the so-called Boltzmann formula. Now the Boltzmann formula gives the ratio of the probability of finding the phonon in the one phonon state and the ground state. This is what you are going to get. They are related by this expression. And now in the steady state, you know the upward transition, number of upward transitions should be equal to the number of downward transition. So utilizing this condition, this particular condition, you can write gamma plus, ratio of gamma plus and gamma minus would be equal to P1 by P0, and already we have the expression for gamma plus and gamma minus. We have already have these expressions there, and utilizing all these expression, we are going to get this particular equation. Okay, now utilizing the fact that the thermal phonon number or NTH or mean phonon number is given by this particular formula, which we all are aware of, and from here you can find out what is e to the power minus s bar omega m by kBt, that you can write in terms of the mean phonon number, and that is going to give you n bar divided by n bar plus 1, and utilizing this you can get this particular formula, and this gives you the ratio for the, basically you are going to get the mean phonon number in terms of all the relevant parameters of the system, and from here you can find out what should be the optimal parameters so that you can get minimum number of phonons in the mechanical oscillator, and that can be obtained if you have this condition. If your cavity decayed kappa is much smaller than omega m, that means the mechanical resonance frequency, and this is known as the resolved sideband regime. In the resolved sideband regime, and if you set this detuning to be equal to omega m, okay, minus delta is equal to omega m. In fact, it basically means that the optical cavity, that optical oscillator has the oscillation frequency matches exactly with the resonance frequency of the mechanical mode or the phonon mode, and apart from that, if you have kappa much less than omega m, then you can simplify this particular expression and you are going to get this particular quantity here, this equation, and from here because kappa is much less than omega, you can eventually obtain that minimum number of phonon that can one obtain considering all this quantum mechanical restriction is this much. So this is the ultimate number of phonon number you can obtain in the resolved sideband regime. Now, having studied the ground state cooling of the mechanical oscillator, let me go back to the linearized optomechanical Hamiltonian once again to understand some more optomechanical phenomena. So we have the Hamiltonian in this form: H is equal to H per delta A dagger A plus H per omega m B dagger B minus H bar Z A plus A dagger B plus B dagger. This is our linearized Hamiltonian. However, this time while I am writing, I am not writing this minus sign because I am now redefining my detuning parameter delta as omega 0 minus omega L. Okay, this you please keep in mind. Now let us transform this Hamiltonian by applying the unitary transformation. U is equal to e to the power I delta A dagger A t e to the power I omega m B dagger B t. Then the new Hamiltonian is going to be H tilde is equal to U H U dagger minus I H per U delta U dagger delta t. You can obtain by explicit calculations and invoking the Hausdorff-Becker formula, which we have done so many times. The transform Hamiltonian you can write in this form. H tilde is going to be equal to minus h per z a dagger b e to the power delta minus capital omega m t. You will have four terms, then plus a b dagger e to the power minus I delta minus omega m t. Then you will have term a b e to the power minus I delta plus omega m t, and a dagger b dagger e to the power I delta plus omega m t. So this is the new Hamiltonian, new form of the Hamiltonian we are having after this unitary transformation. Please note that by making the unitary transformation, we are actually going over to the interaction picture so that we can focus on the optomechanical interaction a bit more closely. So first let me discuss the phenomena. Two phenomena we are going to study. The first phenomena that we are going to study by setting delta, the detuning parameter delta is equal to capital omega m, and this condition actually implies that laser is red detuned because of the fact that delta is equal to, as per our new definition, is omega 0 minus omega L is equal to omega capital omega m. This implies that omega L is equal to omega 0 minus capital omega m. That means the laser frequency is less than the optical resonance frequency omega 0. That means the laser is red detuned. Okay, that's why when we are setting the detuning parameter at capital omega m, that means the laser is red detuned. Now putting this delta is equal to omega m in this Hamiltonian, new Hamiltonian, you will see that is going to, you are going to have terms AB and A dagger B dagger. These two terms are going to oscillate twice that of the frequency of the mechanical oscillator, twice omega m. That means these are very highly oscillating term, and we can ignore this highly oscillating term, and these terms would now have this explicit time dependence will go away when we are setting delta is equal to omega m. Therefore we are going to get the Hamiltonian, new Hamiltonian under this condition that delta is equal to capital omega m. We are going to get minus h bar 0 a dagger b plus a b dagger. So this is the Hamiltonian that we are going to get, and this Hamiltonian is quite useful and important, and this Hamiltonian has a name, and it is called the beam splitter Hamiltonian, and it will be clear to you why it is said so. It is called beam splitter Hamiltonian, very useful Hamiltonian. Now we can immediately write the equation of motion for the optical mode and the mechanical mode using this Heisenberg equation of motion, IH per dA dt. Please remember that here we are not considering quantum noise and the dissipation phenomena. We are completely focusing on the optomechanical interaction only, and this is the Heisenberg equation for the optical mode. And if you do the maths, very simple commutation algebra, if you do, you will have minus h per z a dagger b plus a b dagger. You can show, and very easily you will get this equation. You will get dA dt is equal to I z b. this is one equation you will get. And similarly from the other Heisenberg equation for the mechanical mode, I h bar dB dt is equal to bh, this is h tilde actually, the beam splitter Hamiltonian we are taking, but I hope you understand. Maybe I may not write it all the time h tilde. So using this you are going to get this differential equation for the mechanical mode, dB dt is equal to IgA. Alright, so we have these two coupled differential equation, and one can easily solve these two coupled differential equation. The solution is trivial. Please try to get it, and you will get the solution in this form. A of t would be equal to a of 0 cos zt plus I b of 0 sin zt, and you will get b of t is equal to b of 0 cos zt plus I a of 0 sin zt. Okay, this is what you will get. Now these solutions imply that at arbitrary time the modes a and b are mixtures of their initial values. Now at a special time t is equal to, say, t0 is equal to pi by 2z, you will get these solutions. The a at t is equal to t0, you are going to get it would be I b0, and b at this special time t is equal to t naught, you are going to get it as I a of 0. Okay, what it mean? This mean that the modes have exchange values. It implies the modes have exchanged values. This feature can be exploited to transfer the states from optical mode to phonon mode. So this feature is very important for state transfer, and it is heavily exploited for state transfer purposes. Okay, let me repeat again. This feature can be exploited to transfer the states from optical mode to the phonon mode. In fact, the optical information can be written to and read from the mechanical mode. Now let us consider the second case. Now this time let me set my detuning parameter delta at minus omega m, and this is clearly the case of blue detuning, and please do the analysis and convince yourself that yes, indeed this is the case of blue detuning. In this case, as you can see from the transform Hamiltonian, this time the terms that are going to oscillate very highly are going to be a dagger b and ab dagger. Okay, these two terms are going to oscillate very highly at the twice the oscillation frequency of the mechanical resonance frequency. So therefore these two terms can be discarded, and you are going to get the Hamiltonian as h is equal to minus h bar z ab plus a dagger b dagger. This is what you are going to get, and this Hamiltonian is called squeezing Hamiltonian. This Hamiltonian is called squeezing Hamiltonian, and it will also be clear to you why it is said so. And once again you can obtain the equation of motion for the optical mode and the mechanical mode, and you can use the Heisenberg equation of motion to obtain the equation of motion for the optical mode as a dot is equal to Ig b dagger and b dot is equal to Ig a dagger. Okay, these are the couple differential equations that you are going to obtain under the condition when you are setting the detuning parameter delta at minus omega m. Now the general solution of this coupled differential equation can also be obtained in a straightforward way, and you will get the solutions in this form. You will get a of t is equal to a of 0 cos hyperbolic term is now going to appear, cos hyperbolic gt plus I b dagger 0 sine hyperbolic gt, and b of t is equal to b of 0 cos hyperbolic gt plus I a dagger of 0 sine hyperbolic gt. Okay, this is what you will get. These solutions should remind you about our discussion on single mode squeezing. You may recall that in the context of single mode squeezing, which we have discussed in the context of harmonic oscillator earlier, so we get this expression when the mode is squeezed along, the optical mode is squeezed along the x direction. We got this expression, if you recall, a of t is equal to a of 0 plus you will have cos hyperbolic r here, cos hyperbolic r plus a dagger of 0 sine hyperbolic r. Now squeezing here is happening along x direction, okay, along the x quadrature. This is what you will have, this you should recall. However, now we are having a bit complicated situation. Now we are having two modes in the present case, and it is the case of two mode squeezing. It does not mean that both modes are getting squeezed, rather the sum or difference of the normal coordinates of the two oscillators written in terms of their respective quadrature operators are either getting amplified or squeezed. In fact, we can show that the normal coordinate x1, sum of the normal coordinate x1 plus x2 belonging to these two oscillators, optical oscillator and the mechanical oscillator. I will define all these terms. X1 plus x2, sum of the normal coordinates is equal to x1 at time 0 plus x2 at time 0. This is going to get amplified, sum of the normal coordinates getting amplified, and the difference in the normal coordinate x1 t minus x2 t, these are quadratures in a way, and you are having here x1 0 minus x2 0, it is going to be squeezed e to the power minus gt. Now here we are having x1 is defined as, it's a mixture of the position quadrature xa of the two oscillator xa plus xb. X1 is xa plus xb, x2 is ya plus yb, this is the momentum quadrature, and xa is defined as, this is the quadrature operator for the optical oscillator, that is a plus a dagger by root 2, and xb is equal to b plus b dagger by root 2, and ya is equal to a minus a dagger by I into root 2, and yb is equal to b minus b dagger by root 2 I. While defining these quadratures, it is done in such a way that a dagger is equal to 1 and b dagger is equal to 1 is maintained. Okay, the squeezing of the relative oscillator coordinates point towards the presence of strong quantum correlations between the optical and mechanical modes. This is an important point to remember. So let me write here, the squeezing between the relative coordinates, that means x1 minus x2, relative coordinates indicates presence of strong quantum mechanical correlations between the optical and the mechanical mode. Optical and the mechanical mode. Okay. In fact, one such strong quantum correlation is the so-called optomechanical quantum entanglement. Optomechanical entanglement is a very strong quantum correlation. So let me give you a very brief idea. We are not going to discuss in detail. This is basically the entanglement between the optical mode and the phonon mode. To give you a very brief idea about it, let me explain it this way. You know that this radiation pressure force is the reason because of which the movable mirror is getting displaced. Okay, because of the radiation pressure force, the movable mirror get displaced. This radiation pressure force depends on the number of photons in the cavity. So let me write here, because radiation pressure force is dependent on the intensity of the radiation, and intensity is again dependent on the number of photons. Radiation pressure force depends on the number of photons in the optical cavity, and also you know the displacement of the movable mirror, depends on the strength of the radiation pressure force, right? Radiation pressure force, and the strength is measured by the number of photons present there. Now, for example, when there is no quanta in the cavity, that means when n is equal to 0, this mirror is not getting displaced. But if there is a photon, I'm giving you a exaggerated picture, by the way, displacement is not like this, but okay, you just get the idea that if number of photon is getting now increased, say n is equal to 1, the mirror is getting displaced further, and if number of photon increases further, then it goes on, the displacement goes on increasing further. Okay, so this is what you have. This situation implies that if you try to write down the overall state function of the optomechanical system, then you can write it as a superposition of the photon state. Say photon state is going from n goes from 0 to infinity, and because the mirror, the mechanical mirror or the oscillator is in the ground state, and it remains in the optomechanical ground state, as you know, because we have to cool it. And when it is getting displaced, because it is in the ground state, and displaced ground state is a coherent state, so the mechanical oscillator state can be represented by the coherent state. Say, let me write it as beta n, and because this coherent state is dependent on the number of photons in the cavity, and there may be some phase term may also be there, say I of phi of t, it may be there. So this is the overall quantum state of the optomechanical system. Now, in no way you can write the overall state as the product state of the photon and the phonon state. You cannot write it as a product state of photon state and phonon state, because the phonon state is explicitly related to the photon numbers or the photon state. So this implies that psi of t is an entangled state. So this is basically the basic idea behind optomechanical entanglement. Now let me quickly digress a bit and let me tell you how entangled photons are generated in laboratory. What is the process? The most popular process is the so-called spontaneous parametric down conversion. So this is the process by which entangled photons are created in laboratory. Spontaneous parametric down conversion, in short it is called SPDC. I should have actually talked about this particular process earlier, but just because I'm discussing quantum entanglement, it just reminded me, okay, just to mention you about this process. Now actually you know about that sum frequency generation or difference frequency generation. These are the concept from nonlinear optics. For example, you know that if you have a nonlinear crystal, the second harmonic generation, all of you have heard perhaps, that when a optical signal at frequency omega is passing through a nonlinear crystal having susceptibility chi2 or the second order nonlinearity, at the output you may get, subject to the appropriate condition, satisfying appropriate conditions, you may get double the frequency of the input signal. This is called second harmonic generation or HHG. In the case of spontaneous down conversion, which is also a nonlinear optical process, so again you are having a chi2 crystal, nonlinear second order crystal is there, and in this crystal a very strong pump is, a very high energy pump signal is getting incident on the crystal, and this pump photon spontaneously splits into two low energy photons, basically low energy photons called signal and idler. These photons are called, low energy photons are called signal and idler, and these signal and idler so produced are entangled to each other. And what is remarkable is that this process is a parametric process. So in this process, both energy and momentum are conserved. So in SPDC, both energy and momentum are conserved. This is the reason why this process is called spontaneous parametric down conversion. Parametric because energy and momentum are conserved. Let me tell you once again that the signal and the idler so produced are entangled to each other. Please once again note that this information of spontaneous parametric down conversion I am providing you is in the context of entanglement only. It is not related to optomechanical entanglement. Let me stop here for today. We have almost completed our discussion on cavity optomechanical system. In the next lecture, we are going to do some problems on James Cummings model and cavity optomechanical system. So see you in the next lecture. Thank you so much.